Hi, my name is Jack Ellerbeck, and today I'll be talking to you about proving quadratic reciprocity with cyclotomic fields. First, I'm going to tell you about the quadratic reciprocity law and why it's useful. I'm going to give you some background information that will build off of abstract algebra and give you some cool techniques from algebraic number theory. And then we're going to go into the proof of the quadratic reciprocity law. So first, we're going to define something called the Legendre symbol. And this is a function of a and p, where a is any integer and p is an odd prime. And we're going to say that a over p is 1 if a is congruent to b squared mod p for some integer b. We're going to say it's equal to -1 if a is not congruent to b squared for any b mod p. And we're going to say it's 0 if a happens to be a multiple of p. And some terminology, if a over p is 1, that is if a is equivalent to b squared mod p, a is called a quadratic residue mod p. So as an example, let's consider maybe 2 and 7. So what is this? Well, 2 doesn't look like a square number, but remember we're reducing mod 7. So 2 is actually equivalent to 9 mod 7, which is 3 squared. So it turns out that 2 is in fact a quadratic residue of 7 because it's equivalent to 3 squared in mod 7. So we can use the idea of the Legendre symbol to ask some questions like, does 6 have a square root in this finite field? Well, that's the same thing as asking whether this Legendre symbol is 1. And you can imagine that we can also use it to talk about things like irreducibility of these polynomials over finite fields. The Legendre symbol allows us to succinctly state some questions about whether things are squares mod a number. So using the Legendre symbol, we can state the law of quadratic reciprocity, which comes in 3 parts. And what this allows us to do is calculate the Legendre symbol for any number mod p. So the first part tells us when -1 is a quadratic residue of p. So as an example, is -1 a quadratic residue mod 5? And it turns out that it is because -1 is equivalent to 4, which is 2 squared. And that checks out because 5 is equivalent to 1 mod 4. If it were congruent to 3 mod 4, then we would get -1. The second part tells us when 2 is congruent to a square mod p. And then the third part is the really elegant part, and this is the part we're going to prove today. It turns out that q is a quadratic residue of p as long as p is a quadratic residue of q. There's this reciprocity here. This part is true when at least one of p and q is 1 mod 4. If we're in the case when p and q are both congruent to 3 mod 4, then we get that q is a quadratic residue of p as long as p is not a quadratic residue of q. So this allows us to flip over the Legendre symbol if one is more easy to calculate than the other. And in the other case, we can flip over the Legendre symbol and all we have to do is multiply by -1 out front. So these 3 facts, along with this other result that tells us the Legendre symbol is multiplicative, allow us to calculate the Legendre symbol for any number mod p. And by multiplicative, what we mean is that if we have a over p times b over p, that's always equal to ab over p. Okay, so using those results, see if you can pause the video here and calculate the Legendre symbol for 314 over 71. Okay, so let's try it ourselves. Obviously, this isn't going to be easy to look at right off the bat and figure it out. We could try to reduce 314 mod 71, but that looks sort of hard. But I know that 314 decomposes as 2 times 157. And using the fact that it's multiplicative, we can write this. Okay, now we know that 2 is a quadratic residue mod 71 based on the last slide, as long as this is 71 is 1 or 7 mod 8. Since it's 7 mod 8, we get that it is in fact a quadratic residue. So this evaluates to 1. And this looks a little harder to figure out, but we can reduce mod 71. So 157, you can check, is equivalent to 15 mod 71. So this is 15 over 71. And we can again decompose into its prime factors, 3 over 71 times 5 over 71. And now we can really use that third part of quadratic reciprocity, the really elegant part, which tells us that 5, because 5 is 1 mod 4, we can flip over the Legendre symbol and get the same answer. Since 3 and 71 are both 3 mod 4, we can do 71 over 3, but we have to multiply by 1 out front. Now we can reduce mod 3 and 5 respectively, so we're going to get negative 1 times 2 over 3, and 71 over 5 gives us 1 over 5. Now 1 squared is always 1, so it's always a quadratic residue no matter what the bottom is. So this is definitely 1. And 2 over 3 we can check, that's negative 1 based on our theorem. So what we get is 1. So without having to worry about squaring things and figuring things like that out, we were able to use the theorem of quadratic reciprocity to figure out that 314 is equivalent to a square mod 71. So this was conjectured a little bit before Gauss, but Gauss proved it himself. He was the first to prove it, and he considered it one of the most elegant and fundamental results he had ever shown. He came up with at least 6 proofs by himself. And since him, over 240 proofs have been published. Many of them are recent, and they all come from various different areas and angles from math. We've got analytic number theory proofs, elementary proofs, algebraic number theory proofs, and every time a new proof is discovered, it gives us a little bit more insight into quadratic reciprocity and some more insight into the field of math that the proof came from. You might also be wondering about higher power reciprocity laws, whether there's a cubic reciprocity law or a quartic reciprocity law. And it turns out that there are, and the search for and study of higher power reciprocity laws allowed some folks in the 19th century to prove some results that had to do with Fermat's last theorem, in the sense that in 1847, a man named Lemay thought he had come up with a proof, but Kummer, who had been studying higher power reciprocity laws, had found some results that contradicted Lemay's proof and made Lemay's proof sort of sink. So the idea of reciprocity has results that are wide-reaching in number theory. Okay, so now we're going to go into some background. Remember from abstract algebra the idea that we can have a tower of subfields, where K is a subfield of L, and these are both fields. And we associate with this extension, with this field extension, some number n. And we're going to talk about cases where n is finite, and this bottom field is the rational numbers q. We call these number fields, and all number fields are algebraic. All finite extensions of the rationals are algebraic. We can write these as q adjoin alpha for some algebraic number alpha. In particular, q adjoin the cube root of 2 is a number field. And we know that it's algebraic because the cube root of 2 is the root of this polynomial. There's a couple families of number fields we like to talk about. Quadratic fields are one great example. These are when we take q adjoin root d for d some square free integer. So what we have is q adjoin root d lying on top of q. And what this field looks like is the set of all a plus b root d, where a and b are rationals. So that's what one of these number fields looks like. So these ones here that have degree 2. The other kind we're going to talk about are cyclotomic fields. And this is when we adjoin zeta p, which is a pth root of unity. And remember that a root of unity is a number, a complex number, which when raised to the p power equals 1. P doesn't have to be prime, but we're exclusively going to talk about prime cyclotomic fields in this talk. And these end up being p minus 1, degree p minus 1 extensions. So q adjoin zeta p over q can have degree p minus 1. We get this nice interaction between these two types of cyclotomic, two types of fields, cyclotomic and quadratic. We get this relationship where q adjoin zeta p always lies over, when p is prime, always lies over a unique quadratic field. Q adjoin root P star, which lies on top of Q, where P star is some notational shorthand we use to say that we're taking P or negative P depending on whether P is 1 or 3 mod 4. So we want to make sure the thing in the square root is always equivalent to 1 mod 4. Okay, keep an eye on this theorem because this is going to come back and be important for the proof. Now, we're going to talk about rings of integers. And remember that Z and Q have this relationship where Q is the quotient field of the integers. And you might be wondering, well, if we have some field extension, do we also have something like the integers in this extension field? The answer is yes. We call it the ring of integers of K, and we notate it as OK. And OK has the integers as a subring. This relationship here is like the key to algebraic number theory. So what are the rings of integers for the types of fields we've been talking about? When Q is this quadratic field, when K is this quadratic field, then OK, the ring of integers, sort of comes in 2 flavors depending on if D is 1 mod 4. If D is 1 mod 4, then it looks like this set, where A and B are integers with the same parity, either both odd or both even. And if D is not 1 mod 4, then it's really simple. It's just A plus B root D, where A and B are integers rather than rationals. And when we have a cyclotomic field, the ring of integers looks like this. And don't be too scared by this. Basically, we're saying it's powers of zeta p, where we have integer coefficients and not rational coefficients. So you can see how these might sort of act like integers. And in fact, if you know what a Dedekind domain is, you'll be interested to hear that the ring of integers of a number field is always a Dedekind domain. And that'll give us some really cool properties in a sec. Now we're going to think about prime factorization. And remember that there are numbers that are prime in Z, meaning that they don't factor. And not all of these primes are always, they don't always remain prime when we think about higher number fields, when we think about OK for different number fields. For example, 5 factors in the Gaussian integers, which is the integers like A plus bi, where A and B are integers. This will factor as 2 plus I times 2 minus I. So even though 5 looks prime in Z, it's not prime in this ring here. In this ring of integers. And you have to do some work to show that neither of these elements is a unit in this ring, but take my word for it that neither of them are, and this gives you a non-trivial factorization of 5 in this ring. So sometimes primes aren't prime when you think of different rings of integers. In addition, factorization into primes that are prime in the rings of integers isn't always unique. Like we can come up with an idea of primeness in these rings of integers, even though prime factorization doesn't end up being unique. However, we can figure out that ideals of this ring of integers OK always factor into prime ideals. And that has to do with the fact that it's a Dedekind domain. So recall this definition of a prime ideal. And we get that in Dedekind domains, ideals always factor uniquely, not just factor, but they factor uniquely into prime ideals. And when we take the case of number fields, we get that every prime ideal in a ring of integers of K contains exactly 1 prime in the integers. So for any prime, and this denotes the ideal generated by P, the prime P, where this is a subset of the integers, this lies under some P, which is a prime ideal of the ring of integers OK. So now let's think more about this factorization idea. We can get that the ideal I factors as a product of prime ideals, and they're going to be raised to some powers, some of which might be 1. This is really the picture you should be thinking about here, which is that I lies underneath all of these primes here, these prime ideals. Notice that we always denote the power on the prime as E, E1, E2, etc. We're also going to define this number fi, which if you understand this notation, that's great. You'll know exactly what this means. But all you really need to know is that fi is intrinsic to pi. It has to do with the details of the ring and details about the prime itself, the prime ideal itself. So we call this number the relative degree or inertial degree of the prime ideal pi over the prime p over which it lies. In particular, this could be any ideal, but we're going to think about the case where it's the prime ideal generated by some prime p. So with these EIs and FIs, we get this interesting theorem which says the sum of the products over a factorization gives n, the degree of the field extension. So that for high values of n, that might not mean too much, but in the case where n equals 2, think that there's, notice that there's only a couple ways that this could decompose since these are always positive. We could either have 2 as, 2 times 1, or we could have it as 1 plus 1. And this could be the case where E equals 2 or F equals 2, or this might be the case where E and F are 1. Okay, so this tells us that there are exactly 3 ways that some prime ideal could factor in a quadratic field because it has degree 2. So for example, in the quadratic field Q adjoint root negative 5, we have that the ideal generated by 5 factors as this ideal generated by root negative 5 squared. And when we have a prime ideal squared, we call that ramified. We say 5 is ramified in K in this field. We also have the case where a prime splits. In this case, 3 splits into these 2 ideals. 3, the ideal generated by 3 and 1 plus root negative 5, and 3 and 1 minus root negative 5. And in the top case, we had E equals 2, and in this case, we have E equals 1 and F equals 1. And in this case, with 11, we say that it's inert because really it just factors as itself. It's already prime. And this is the case where F equals 2. So these are the 3 cases you can have in factorization into prime ideals in a quadratic field, remember. We also get this other theorem which tells us that in a quadratic field, we have special cases on when a prime P can ramify. And it only ramifies if D is 1 mod 4, if P divides D, or if D is not 1 mod 4, then it ramifies if and only if P divides 4D. So notice negative 5 is not 1 mod 4. So we have to check if it divides 4 times negative 5, which is negative 20. And since 5 divides negative 20, we expect it to ramify, and neither of these 2 divide negative 20, so we don't expect them to ramify. So that checks out. Okay, now I'm going to give you an overview of the proof, now that you know all that background information. So remember that we're going to have P and Q be odd primes in Z. And I'm going to remind you of what we're trying to prove. And we're going to prove it in 2 steps. First, we're going to show that Q over P is 1. That is, Q is a quadratic residue of P, if and only if Q splits in K, where K is this quadratic field, which remember is the unique quadratic field lying in this cyclotomic field. So also remember that Q splits in K means that it factors as 2 primes. Next, we're going to show that P star is a quadratic residue of Q, if and only if Q splits in K. Now, since these are the same condition, we're going to get that Q over P is 1, if and only if P star over Q is 1. And I claim that this is equivalent to saying this part up here. So this, the way we defined the theorem before, is the same as saying that these 2 are always true in the same cases. So if you want, you can pause the video and try to convince yourself of that. It's not too hard. So unfortunately, the first part is going to take way too much time for me to prove. It's not out of the scope of this talk. I spent a lot of time learning it, but unfortunately I don't have time. It uses a lot of hard-hitting algebraic number theory stuff. So I'm going to give you a brief overview, but we're really going to focus on 2. We're going to dig into that. So first, I'll give you an overview of part 1. The idea here is that the Galois group of L over Q is isomorphic to the finite field, the multiplicative group of the finite field P, the Pth finite field. And we have a certain automorphism, automorphism sigma Q, which is associated with Q in this finite field. And this automorphism, it turns out that Q is a quadratic residue mod P, as long as sigma Q fixes K, as in K is the set of fixed points under this automorphism. And because sigma Q turns out to be what's called a Frobenius, it has some properties that we can prove that says that it fixes K if and only if Q splits in K. So what we get is that Q over P is 1 if and only if Q splits in K. And that's the first part of the proof done. I would love to talk more about this proof with anyone who's interested. It's super interesting. The Galois theory part is really cool. Algebraic number theory part is really cool. So please let me know. Send me an email or run into me in person, whatever it is you want to do. It's really cool. Now let's get into the second part of the proof. We're going to first prove this direction. Q splits in K implies that P star over Q is 1. If Q splits in K, remember that means that Q factors as P1, P2. That means we can take one of these ideals, P, and we'll know that the ideal generated by Q is a proper subset of P. That means we can take any element of P that, we can take an element out of P that's not in this ideal generated by Q. So we can find elements of this ideal which are not multiples of Q. Now you might remember that in the case of 1 mod 4, which is what we're in, we have to make sure that sometimes we have to divide by 2. However, since 2 is not a multiple of Q, we can multiply any element by 2 and it still won't be in the ideal generated by Q. So hopefully you're convinced that that this is truly a general element of this ideal. So now we're going to take that element, a plus b root p star, and we're going to multiply it by this other number, a minus b root p star. And because this is an ideal, whatever product we get, which turns out to be a squared minus b squared p star, you can convince yourself of that with FOIL. This has to be in the ideal P, because this first element is in P, and that's how ideals work. But notice that these are all integers here, so it's in the intersection of P with the integers. And keep in mind that the intersection of P and the integers is exactly the ideal generated by Q. So that tells us that Q divides a squared minus b squared p star, because they're in that ideal. So now that we have Q dividing this difference, we can say that b squared p star is congruent to a squared mod Q. What we'd really like to do is sort of divide by b squared, but we can't do that unless we know that b squared is relatively prime to Q. So let's suppose for contradiction that Q divides B. Well, that would mean this side is 0, which means this side also has to be 0. So Q must then divide A. But that would mean Q divides A squared, sorry. This would mean that Q divides A plus B root P star, because it divides both of these coefficients. But remember, we chose A plus B root P star so that it wasn't in this ideal, which means this is a contradiction. Therefore, Q cannot divide B. Okay, so now that it doesn't divide B, we can safely divide by B squared, or even better, multiply by the inverse of B squared in Z mod QZ to get B squared P star is equivalent to A squared if and only if P star is equivalent to B inverse A squared mod Q. And that means we're done with this part of the proof, because we've shown that P star is equivalent or congruent to some integer squared mod Q. And that's the definition of this. So now we're done with 2a. Now we're going to assume that P star is a quadratic residue of Q and show that Q must split. So consider this ideal generated by A minus root P star and Q in OK. And notice that this divides the ideal generated by Q because every multiple of Q has to be in this ideal. Now we're going to try to rule out all the cases except for the one where Q splits. So we could have that Q decomposes into P and P prime, and this is what we want. We want to show that Q splits into two different ideals, but we have to consider the other cases. It could be that Q decomposes into P squared, which is to say Q is ramified. We also could have the case where Q sort of divides P because it's inert, that P is actually the same as Q, as the ideal generated by Q, pardon me. Or we could have the case where this ideal P isn't really prime at all and is in fact equal to the trivial ideal, which is really the whole ring. And this is the case, these three cases we want to eliminate. So remember that we have a theorem that says Q can only ramify if it divides, in this case, P star, because P star is 1 mod 4. But because P and Q are prime numbers that are different, we know that it can't be ramified, and therefore we can eliminate that case. Now we have the case where Q is actually the same ideal as P. What that would mean is that this generating element is redundant. But that can't be the case because A minus root P star is not a multiple of Q, which means it can't be redundant. And this is definitely a different ideal. So that eliminates that possibility. Now we have to consider where P is actually the same as the ideal generated by the identity. If it were the ideal generated by the identity, then we could expect to multiply it by any other ideal and get the same original ideal back. In particular, consider the ideal generated by A plus P star. We're going to multiply it by our ideal P, which is A minus root P star, and Q as its generators. And we're going to distribute this multiplication to those generators. And what we get as the first generator is A squared minus P star. And as the second, we get Q times A plus root P star. And now we want to check, is this ideal equal to this ideal? Well, this first generating element here, A squared minus P star, we know that that has to be a multiple of Q because those are congruent mod Q. So this is really CQ for some integer C. And this part here is definitely a multiple of Q. So that implies that this ideal here is some multiple of the ideal generated by Q. But that would imply that this original ideal is a multiple of the ideal generated by Q. But because A plus root P star isn't a multiple of Q, this is impossible. Therefore, this ideal down here has to be different than the first ideal, which means that our ideal P is not equal to the trivial ideal. Therefore, we can eliminate that case, and we're left concluding that Q splits. So we showed that Q is a quadratic residue mod P as long as Q splits. And we just showed that if Q splits, then Q splits if and only if P star is a quadratic residue mod Q. And that concludes the proof. I'd like to thank you all for watching. I also want to acknowledge the book Number Fields by Marcus, from which this proof was derived. I also want to thank the Cornell professor David Zywina, because he has some class notes published online that include this proof and some really accessible background. And of course, I want to thank Professor Pacelli for advising me through this talk and helping me with any questions along the way. Thank you all for watching. That's it.